This lab is on OSPF version 2, which involve OSPF communicating IPv4 addresses between all the routers itself. And this communication basically involves 3 routers, which involve R1, R2, and R3. In advance, I already finished off the configuration of A to G. Okay, except for R3, which is going to show some basic configuration which involve the configuration of IP address on the interface itself. So let's now go to R3. Okay, as I mentioned, I already configured things like hostname, no IP domain lookup, line console 0, line VTY 0, and on top of that also the banner MOTD. Let's go into gigabit interface 0/0. Okay, and do the IP address for the interface, which is IP at 192.168.20.3.1. Subnet mask is 255.255.255.0. Do a no shut to enable interface. Next, interface S000, which is a DC interface. IP at 192.168.13.2, 255.255.255.252. Clock rate, which is given as 108,000, and no shut to bring up the interface. And the last interface to configure will be serial S0/0/1, IP at 192.168.23.2, 255.255.255.252 again, and do a no shut to bring up all the interface. As can be seen that all the links are now green. Okay. So after this, we're going to start configuring for OSPF. I can see that to configure OSPF, basically we'll start out with router OSPF1. Okay. And the differences between OSPF and RIP version 2 is that instead of just specifying the network followed by network address, we are going to be more specific in specifying the network address comes with which subnet mask. But instead of using subnet mask, we are going to make use of wildcard mask. And you can see that here I actually input 2 methods to actually calculate what is the wildcard mask to be used with the subnet mask that is given. You can see that the first example, if we have a subnet mask of /24, which in this case is 255.255.255.0, basically we just need to use 255.255.255.255 minus of the subnet mask 255.255.255.0, which is equivalent to /24. We will get a remaining value of 0.0.0.255, and this will be known as the wildcard mask to be used, which represent a /24 in OSPF. Another example, subnet mask of /30 or decimal equivalent is 255.255.255.252. Same thing, 255.255.255.255 minus of 255.255.255.252. 255 minus 255 will give you 0. 255.255 will give you 0. 255 minus 255 will still give you 0, and 255 minus 252 will give you a 3. So a /30 subnet mask will give a wildcard mask equivalent of 0.0.0.3. Okay. And another explanation behind a wildcard mask, basically I always have to say that a wildcard mask is the inverse or opposite of subnet mask. Why is this so? Basically we can see it from the way that the binary digit has been calculated. We know that a /24 is 255.255.255.0. When converted to its binary equivalent will be 8 bit of 1 followed by 8 bit of 1 followed by 3 8 bit of 1, which is 24 bit of 1 followed by 8 bit of 0. When we invert the 1 to become 0 and 0 become 1, we will get a wildcard mask of binary representation of 80, 80, 80, and 81, which when converted back to decimal will give us a 0.0.0.255. So always remember that for OSPF, we are more specific in specifying what are the portion of the network to be used by specifying the subnet mask to be used. But in this case, we are making use of the wildcard mask. So let's start by going to R1 and configure our OSPF. So in this case, as I mentioned, can always make use of the routing table to help us to configure our dynamic routing protocol. Let's do a show IP route. Similarly as what I have taught before in RIP version 2, look at all the C. In this case, I have a 192.168.1.0 network, .12 network, and .13 network. Okay, we're going to start off by doing router OSPF1. The 1 basically is the process ID, which is local significant, recognized by the router itself only. Okay, always remember that OSPF must always have a process ID, and normally we will just use 1. Followed by network. I'm going to specify the first network, which is 192.168.1.0. Previously for read version 2, we just need to stop here, but for OSPF we need to specify a wildcard mask, which in this case left 24, which we have calculated before, will be 0.0.0.255. Okay, followed by specifying the area that this network is supposed to be in, which is area 0. And area 0 is also known as the backbone area in OSPF. Same thing, do it for the other two network, 192.168.12.0. In this case, less 30 will be 0.0.3, area 0. Same thing for the last network, 192.168.13.0, 0.0.0.3, area 0. And that's it for OSPF, as can be seen from here. And similarly, in OSPF, we also have the passive interface command, which is to stop any routing information from being sent out through the interface which the other device is not using. In this case, for gigabit interface, 0/0 is not required for the interface to send any information out, as it's basically just a PC. Okay, let's do it for R1. Let's go to R2. Do the same thing, do a show IP route. Okay, and start off by a router, OSPF1 network. Let's do the first one, 192.168.2.0, 0.0.0.255, the wildcard mask, followed by area 0. Next network, 192.168.12.0, 0.0.0.3 for /30, area 0. And last but not least, network 192.168.23.0, 0.0.0.0.3, area 0. Okay, and last but not least, for R3, do a show IP route again. Okay, then router OSPF1 network 192.168.3.0, 0.0.0.255, area 0. Network 192.168.13.0, 0.0.0.3, area 0 again. And network 192.168.23.0, 0.0.0.0.3, area 0. Okay, and that's it. We have actually configured all the network to be involved in OSPF version 2. Let's do a show IP route again. Okay, to see all the network that has been known by all the router. You can see that the code that is representing OSPF is 0, and mean distance is 110, and the metric that involve the route is basically based on bandwidth, which is also known as the cost. Okay, so just now we actually disable the sending of routing information through gigabit 00 interface on R1. Okay, some other command that you want to take note of when it comes to OSPF other than show IP route are command like do show IP OSPF neighbor, GHBOR. Okay, which will look at who are the neighbor that is connected to the router itself. In this case, R3 is connected to the router, and the router ID, which uniquely identified router, is 192.168.13.1 and 192.168.23.1, which correspond to R1 and R3. Some other command like show IP protocol. Okay, will show you what are the dynamic routing protocol that is running, what the process ID, and what is the network that is involved in the OSPF process. Do show IP OSPF. Okay, will show you same thing, what is the OSPF process that has been configured with the ID of the router that is running the OSPF. In this case, for R3 is 192.168.23.2. Okay. So other command that you may want to take note of, okay, is other than knowing that passive interface for the individual interface, we can also configure all the interface to be passive all at once, okay, by doing a passive interface default. So let's try out on R2. In this case, let's go to R2. Just already on R1, so let's just ignore R1 for time being. Okay, make sure that you're in the router OSPF1, okay, and passive interface default. Okay, so when you do a default, basically you're telling all the interface, okay, to be on passive interface mode. But in this case, if we take it that all the interface are on passive mode, that means that S000 and S001, we are supposed to communicate OSPF information to R1, R3 are not sending information. Okay, that is why we actually need to disable by doing a no passive interface S000 command and no passive interface S001 command. Okay. Something to take note of when you are doing a no passive interface command, you can see that just now when we did a passive interface default, that means that 000 and 0001 are not sending OSPF information. You can see that the neighbor is down to mean that OSPF process are not running for both interface to R1 and R3. But once we do the no passive interface, okay, the adjacency process kickstart again for both R1 and R3. Okay, so these are some of the commands that you may want to take note of. So other than this, we know that just now all the router has been assigned with its default router ID, which is the IP address. But there is a method for us to actually change it also by using the router ID information. Make sure you are in the router OSPF configuration, okay, and do a router ID. Okay, say for R1 according to lab, we are going to set it to 11.11.11.11, okay, to basically specify what is the IP address on the router. Okay. So basically there are three methods for a router to get hold of a router ID. Either to make use of the router ID command, okay, or the loopback interface IP address, or the IP address of the interface. So in this case, don't do the router ID command first. Okay, let's start doing the loopback address first. So in this case, we are going to make use of 1.1.1.1 for R1, 2.2.2 for R2, and 3.3.3 for R3. Okay, so interface LO 0. Okay, for R1, do the IP address 1.1.1.1 followed by 255.255.255 with /32. Do the same thing for R2. Interface LO0, IP address 2.2.2.2, 255.255.255.255, no shard. Same thing for R3. Interface LO0, IP address 3.3.3.3, 255.255.255.255, no shard. Okay. So when you do a show IP protocol, okay, show IP protocol, you'll see the router ID are still the same. So how can we actually refresh it? Okay, make sure you save your configuration by doing a WR and do a reload. Okay, and let's wait. While waiting, let's do it for R2 also. Reload. Let's do it for R3 also. WR, reload. Okay, let's go back to R1. Cisco, enable class, show IP protocol. Okay, you can see router ID has now been changed to 1.1.1.1. Okay, you can see that the same process also happened for router 2 and router 3 similarly. So the last, as I mentioned, the third alternative way to configure a router ID for OSPF basically is by making use of router ID command. So let's do it now. router OSPF 1 router ID. In case let's change to 11.11.11.11 as specified in your lab. Okay, same thing for R2. Config T router OSPF 1 router ID 22.22.22.22, and last but not least for R3 Cisco enable class config T router OSPF 1 router ID 33.33.33.33. And basically these are some of the methods that you can actually change the router ID to uniquely identify the router that is sending out the information. Okay, other than that, let's look at our routing table. When we look at our routing table, we know that all the different routes that has been propagated by OSPF have its own metric. Okay, and how do we inference this? As we know that, okay, the way that we inference the metric, okay, in OSPF is by the use of bandwidth. So in this case, as we know that the default bandwidth or the clock rate that we use on the serial interface are by right is 128. But when we do a show interface, okay, for the interface itself, you can see that the bandwidth itself is not actually 128. So let's inference it. Go into interface 000. Okay, do a bandwidth command to actually inference how the bandwidth is on the interface. Then do a show interface again. Take a look. You can see that now the bandwidth has changed to 128 as compared to previously is 1544. Okay, do a show IP route again. Okay, you can see that the metric has actually significantly changed. Okay, for the different network, just now is from 165, now it's been changed to 128. So this is actually how we actually manipulate the bandwidth, okay, to correspond to how the metric is being used in OSPF. And since all the clock rate on the serial interface are of 128,000, let's change all of them. Okay, for here we have really changed serial interface 000. Let's change 001 bandwidth to accurately represent the bandwidth itself. Same thing for R2 interface S000 bandwidth 128, interface S001 bandwidth 128. Same thing for R1 interface S000 bandwidth 128, interface S00/1 bandwidth 128. Okay, do a show run to verify. Okay, you can see that my bandwidth has been changed to 128. So this is one of the methods to actually change the bandwidth of the interface. Okay. Another way to basically inference the metric is by directly modifying the cost of the link. So we're going to do that. Okay, let's go to R1 and go to interface S00/1. The command basically is IP OSPF cost 1565 as mentioned in the lab, to modify the cost to 1565. Okay, then press enter. Okay, and do a show IP route. Okay, so when you do a show IP route, you can basically see that, okay, the route for 23 network has been changed to a number that is terms of 1562. Okay, which is how we actually modify the OSPF cost, or manipulating how metric determine the best path to its destination network. And basically this is how OSPF version 2 works.